Phase diagrams are a way that we can represent all the phase changes that occur for a particular substance. And I'm showing here the general form that a phase diagram takes. And a phase diagram for a particular substance will be a graph of pressure on the y-axis versus temperature on the x-axis. And so you have lines within the graph that divide the different phases of the substance. We put the solid phase, we have the solid phase at this portion of the graph, and it's separated by a kind of Y-shaped structure. And the liquid phase goes here, and the gas phase is in this region. All right, so the lines represent equilibrium between phases. So this line here represents the equilibrium between the solid and the gas phase. The line here represents equilibrium between the solid and the liquid phase, and this line here represents that between the liquid and a gas. There is a point where all three of the lines come together, and that is known as the triple point. So there's one particular point where the solid, the liquid, and the gas are all in equilibrium together, and there's only one point. So the three phases are in equilibrium at the triple point. So there's one particular pressure and temperature where all three phases can be present in equilibrium at the same time. Then there's another point out here which is known as the critical point. And the critical point is where the pressure and temperature are so high that the liquid and gas phase are basically indistinguishable. So pressure and temperature are so high that liquid and gas phases are indistinguishable. So in other words, the gas is so dense that it can't be distinguished from the liquid. All right, and then we can say that anytime you go across this line, the process of sublimation has occurred, solid directly to gas. When you go across this line, the process of melting has occurred if you go to the right, and of course there's the opposite process going the other direction. And if you go across this line from liquid to gas, that's vaporization process. All right, and then we talk about a normal melting point and normal boiling point, and that is what the boiling point and melting point that occur at 1 atmosphere of pressure. That would be considered normal. Okay, the normal melting and boiling point. So depending on what substance it is, will determine exactly where that occurs, but let's say that for this substance 1 atmosphere is here. Then we could say that we go across on, pretend that's a straight line. We go here, and this would be the point where we have normal melting, okay, solid to liquid. So we can go down to what temperature that occurs at, and that would be our melting point, or freezing, either way, depending which way you go, liquid to gas, solid, or solid to liquid. So that's our normal freezing point, and if you keep going out, following that same pressure, 1 atmosphere, then you hit the boiling point, assuming you haven't hit the critical point yet. You hit the boiling point, and that temperature then will correspond to boiling. So that will be the boiling point or vaporization point. Okay, so those are normal freezing and boiling. Of course, freezing and boiling can occur at any pressure, but the one we call normal is the one at 1 atmosphere. All right, and notice that, one more thing to notice on the graph is that the line between solid and liquid is straight, whereas any of the lines that border on the gas phase will be curved, and that comes out of the ideal gas law and the Clausius-Clapeyron relationship, which I'm not going to go into any further detail on. All right, let's look at some examples of specific phase diagrams with specific characteristics. So we'll look at carbon dioxide. Okay, so for carbon dioxide we have this classic Y shape, so we know solid goes here, liquid goes here, gas goes here. And for this substance, the pressure that is normal, 1 atmosphere, occurs somewhere down here, which means that when we go at normal 1 atmosphere pressure, we hit the sublimation point. Okay, we hit T sub. We do not hit a melting point or a boiling point, and that's simply because for this particular substance the Y is high enough up that our normal, at normal 1 atmosphere pressure, we hit the phase change between solid and gas, which is why carbon dioxide sublimes at room pressure. And we don't see liquid carbon dioxide under normal pressure. We would have to go to higher pressure if we wanted to see liquid carbon dioxide. Let's look at another example, which is the phase diagram for water. And water's looks slightly different. And the difference is that it has a Y shape, and we got our solid, liquid, and gas, but we have something that's not very usual, which is that the slope of the solid liquid border is actually a negative slope. For most of them, for most substances, the solid liquid border is a positive slope. Okay, but for water it's a negative slope. And there's not very many other common substances where that is the case. All right, so again, this is pressure going up, temperature going to the right. And so for water, okay, so the negative slope is what's characteristic of the solid to liquid equilibrium. Tells us that for any given point on this diagram in the liquid phase, if you go to lower pressure, you're actually getting a solid. Okay, what does that mean? That means that the liquid is more dense than the solid. Okay, and that's unusual, and that's why solid water, which is ice, floats in liquid water, because the liquid is more dense. So liquid is more dense than the solid, which is unusual, and particularly for water. So that explains why ice floats in water. You may not have thought about it before, but for most substances, the solid phase would not float in the liquid phase. The solid phase would sink. But for water, with this negative slope, the liquid is actually more dense than the solid, and so the solid will float on top of the liquid. Okay, so now you've seen carbon dioxide and water. Oh, and we'll talk about one more thing here about normal boiling. Okay, so we have at 1 atmosphere, we can go across and get to our melting point, and further go across and get to our boiling point, so we can mark these. Here's T freezing, and down here is T boiling, and we know what those two temperatures are. This one is 0 degrees for water, and this one is 100 degrees for water. So we know where those points are at 1 atmosphere. Of course, they would have different boiling and melting points at different pressures. Okay, so let's look at some example problems. We'll look at 2. So stop the video and try this problem. Use the phase diagram for carbon dioxide below, and determine, and this has a nonlinear scale in pressure, so notice that. Determine the phase change that would occur if the pressure were held constant at 6 atmospheres and the temperature is increased from -20 to 31. Okay, so how do we figure that out? The pressure is constant at 6 atmospheres. This is not a linear scale, so 6 atmospheres is going to be not much above that 5.1. So let's say, I can't draw straight, but let's say that's it. Okay, and if you hold it constant at that pressure, and then see what happens between -20 and 31, you'll see they have this phase change. Can't do it. Try once more. Can't do it. Okay, you'll have the phase change that occurs when you cross that line. Okay, and that would be, since this is solid, this is liquid, and this is gas, that would be going from liquid to gas, which would be vaporization. Okay, one more problem with phase diagrams. Here is a phase diagram of some unknown substance, and you're to pick which phrase is true among A through E. All right, let's look at all of them in turn. We have a substance here. We have phases A, B, and C. We should know that this one's solid, this one's liquid, this one's gas. We know that D is the triple point. And here, this one's not labeled, but that would be the critical point. All right, so the substance's liquid form has a higher density than its solid form. That would be like water, okay? And this slope here is negative, just like water. Okay, so the liquid form would be more dense. The liquid form is at higher, for a given temperature, the liquid form is at higher pressure than the solid, which means the liquid is more dense. Okay, so A is true. But let's go on and look at the others. The substance's critical point is labeled D. No, that is the triple point. How about the dashed line? Constant pressure is followed as T is increased. Okay, temperature goes up to the right. The process of vaporization occurs followed by melting. Okay, let's go across this line. First we get to this point, and then we get to this point. This one is solid to liquid. That one would be melting. The next point would be liquid to gas, which would be vaporization or boiling. And this one is backwards. The process of vaporization occurs first and then melting? No, that's backwards. D says, if you follow that line to the right, the process of sublimation occurs followed by condensation. Sublimation would be in this region, solid to gas. That's not where we are in the dashed line. So that is not it. And condensation would be going backwards from gas to liquid. And that is also not correct. So answer A is correct.